For a transformer secondary breaker feeding a bus with multiple other breakers, several layers of protection are recommended. The primary recommendation is differential protection. Since the breaker feeds multiple breakers on the same bus, differential protection is crucial to protect against faults on the bus itself. Differential protection works by comparing the current entering and leaving the protected zone, in this case, the bus. Current transformers, or CTs, are installed on either side of the bus, measuring the current flow. These current measurements are then fed into a differential relay. Under normal operating conditions, the current entering the bus should equal the current leaving the bus. However, if a fault occurs on the bus, such as a short circuit, a significant current imbalance will be detected. This imbalance triggers the differential relay to operate, tripping the breaker and isolating the faulted section. Differential protection is very fast and selective, meaning it quickly clears faults only within the protected zone, minimizing damage and disruption. In addition to differential protection, transformer winding protection is also very important. The breaker should have transformer winding protection to monitor the current and voltage and the transformer's windings. This protects against faults within the transformer itself, which can be caused by insulation breakdown, overheating, or other factors. Transformer winding protection typically includes devices or relays such as overcurrent relays, voltage relays, and differential relays specifically designed to detect faults within the transformer windings. These relays monitor parameters like current, voltage, and the ratio between them, looking for abnormal conditions that indicate a winding fault. When a winding fault is detected, the protection system trips the breaker to quickly isolate the transformer and prevent further damage. The third level of protection is backup overcurrent protection. The breaker can be equipped with overcurrent relays to provide backup protection. These relays measure the current flowing through the breaker and trip if it exceeds a predetermined level. Overcurrent protection acts as a safety net in case the primary differential protection fails to operate or if a fault occurs outside the differential protection zone. It's important to note that overcurrent protection may not be as reliable as differential protection for bus faults because it can be affected by load imbalances on the bus. A heavy load condition could potentially mask a fault, delaying the overcurrent relay's operation. However, overcurrent protection still provides valuable backup and can help to clear faults that are not detected by the primary protection. When implementing these protection schemes, there are several additional considerations. Firstly, the breaker's ground fault protection should be sensitive enough to detect ground faults on the bus. Ground faults occur when a phase conductor comes into contact with ground, and they can be particularly damaging if not cleared quickly. Sensitive ground fault protection can detect these faults early and trip the breaker, preventing further damage. Secondly, the differential protection should be set to trip quickly to minimize fault damage and protect the other breakers on the bus. The faster the fault is cleared, the less stress is placed on the equipment and the lower the risk of cascading failures. Differential relays are typically set to operate very quickly, often within milliseconds, to achieve this fast clearing time. Thirdly, the overcurrent protection should be coordinated with any other overcurrent protection on the bus to avoid unnecessary tripping. Coordination involves setting the overcurrent relays at different points on the bus to trip sequentially, starting with the relay closest to the fault. This prevents upstream breakers from tripping unnecessarily, which could disrupt power to other parts of the system. A coordinated overcurrent protection scheme ensures that only the breaker closest to a fault trips, minimizing the impact on the rest of the system. In summary, for optimal protection of the transformer and the bus, the breaker should be equipped with the following. Firstly, differential protection for fast and selective clearing of bus faults. Secondly, transformer winding protection to detect and isolate faults within the transformer itself. Thirdly, backup overcurrent protection to provide a safety net in case of primary protection failures or faults outside the differential protection zone. By implementing these protection measures and carefully considering the additional factors, you can ensure the reliable and safe operation of the transformer and the bus. To elaborate further on differential protection, let's delve into the technical aspects of how it works. The differential protection scheme relies on Kirchhoff's current law, which states that the sum of currents entering a node must equal the sum of currents leaving the node. In the context of a bus, this means that the total current flowing into the bus from all sources must equal the total current flowing out of the bus to all loads. The differential relay continuously monitors these currents and compares them. To accurately compare the currents, current transformers, or CTs, are installed on all incoming and outgoing feeders of the bus. CT are devices that convert high currents into lower, more manageable currents that can be safely measured by the relay. The CT are typically installed in the line side of the breakers, ensuring that they measure the total current flowing through each feeder. The CT have a specific turns ratio, which determines the relationship between the primary current, the current flowing through the feeder, and the secondary current, the current fed to the relay. For example, a CT with a turns ratio of 1000 to 5 will produce a secondary current of 5 amps when the primary current is 1000 amps. It's crucial to select CT with appropriate turns ratios to ensure that the secondary currents are within the operating range of the differential relay. The secondary currents from all the CT are then wired to the differential relay. The relay sums the currents from the incoming feeders and compares it to the sum of the currents from the outgoing feeders. Under normal operating conditions, these two sums should be equal, or very close to equal. However, if a fault occurs in the bus, a large fault current will flow to the fault location. This fault current will cause a significant imbalance between the incoming and outgoing currents. The differential relay is designed to detect this imbalance and trip the breaker when the imbalance exceeds a predetermined threshold. The threshold is typically set as a percentage of the rated current of the bus. For example, a differential relay might be set to trip when the imbalance exceeds 20% of the rated current. The tripping time of the differential relay is typically very fast, often within 1 or 2 cycles, or 16.67 to 33.33 milliseconds on a 60 Hz system. This fast tripping time is essential to minimize the damage caused by the fault and protect the equipment on the bus. One challenge in implementing differential protection is dealing with CT errors. CT are not perfectly accurate, and they can introduce errors into the current measurements. These errors can be caused by factors such as CT saturation, which occurs when the CT core becomes saturated with magnetic flux, and CT ratio errors, which are deviations from the specified turns ratio. To mitigate the effects of CT errors, differential relays often incorporate features such as percentage differential protection. Percentage differential protection allows a small amount of imbalance to be tolerated without tripping the breaker. The relay calculates the percentage of the imbalance relative to the total current flowing through the bus, and it only trips if the percentage exceeds the set threshold. This helps to prevent nuisance tripping caused by CT errors. Another important consideration in implementing differential protection is the CT wiring. The CT must be wired correctly to ensure that the currents are summed properly by the relay. Incorrect CT wiring can lead to false tripping or failure to trip during a fault. It's also important to ensure that the CT are properly grounded to prevent circulating currents and reduce the risk of electrical shock. In addition to these technical considerations, there are also some practical considerations in implementing differential protection. The differential relay must be properly configured and tested to ensure that it operates correctly. The settings of the relay, such as the tripping threshold and the tripping time, must be carefully selected to balance the need for fast tripping with the need to avoid nuisance tripping. The relay should also be tested periodically to verify that it is functioning properly. Overall, differential protection is a highly effective means of protecting buses and other critical equipment from faults. It provides fast, selective, and reliable protection, minimizing damage and disruption. However, it's important to carefully consider the technical and practical aspects of implementing differential protection to ensure that it operates correctly and provides the desired level of protection. Now let's dive deeper into transformer winding protection. Transformer winding protection is a critical aspect of ensuring the longevity and reliability of power transformers. Power transformers are expensive and essential components of electrical power systems, and their failure can have significant consequences. Transformer winding faults can be caused by a variety of factors, including insulation breakdown, overheating, overvoltages, and mechanical stresses. These faults can lead to short circuits, ground faults, and other types of failures that can damage the transformer and disrupt power supply. There are several different types of protection schemes that can be used to protect transformer windings, each with its own advantages and disadvantages. One common type of protection is overcurrent protection. Overcurrent relays are installed on the primary and secondary sides of the transformer to detect excessive current flow. These relays are typically set to trip when the current exceeds a predetermined threshold, which is based on the transformer's rated current and overload capacity. Overcurrent protection is simple and inexpensive to implement, but it is not very sensitive to faults within the transformer windings. It can also be affected by load imbalances and other factors, which can lead to false tripping or failure to trip during a fault. Another type of protection is differential protection, similar to the differential protection used for bus protection. Differential relays compare the currents flowing into and out of the transformer windings. Any significant difference between these currents indicates a fault within the transformer. Differential protection is more sensitive to winding faults than overcurrent protection, and it is less affected by load imbalances. However, it is more complex and expensive to implement. A third type of protection is voltage protection. Voltage relays monitor the voltage on the transformer windings. Under normal operating conditions, the voltage should be within a certain range. If the voltage drops below or rises above this range, it can indicate a fault within the transformer. Voltage protection is particularly useful for detecting overvoltages, which can damage the transformer insulation. A fourth type of protection is gas detection. Some transformers are equipped with gas detectors that monitor the gases dissolved in the transformer oil. The presence of certain gases, such as hydrogen, methane, and acetylene, can indicate a fault within the transformer. Gas detection is a sensitive and reliable method of detecting incipient faults, which are faults that are just beginning to develop. By detecting these faults early, it is possible to take corrective action before the transformer is damaged. In addition to these protection schemes, there are also some other measures that can be taken to protect transformer windings. These include proper transformer design and manufacturing, regular maintenance and inspection, and the use of surge arresters to protect against overvoltages. The choice of protection scheme depends on the size and importance of the transformer, as well as the specific risks to which it is exposed. For large and critical transformers, a combination of protection schemes is typically used to provide comprehensive protection. Now let's shift our focus to backup overcurrent protection. Backup overcurrent protection serves as a crucial second line of defense in electrical power systems. It's designed to operate when the primary protection system fails to actuate or when a fault occurs outside the zone of primary protection. Overcurrent relays, the workhorses of this scheme, monitor the current flowing through a circuit and trip a circuit breaker when the current exceeds a predetermined threshold for a specific duration. These relays are configured to have inverse time characteristics, meaning that the tripping time decreases as the current increases. This characteristic allows for coordination with other overcurrent devices in the system, ensuring that the relay closest to the fault trips first, minimizing disruption to the rest of the network. Several factors influence the selection and settings of backup overcurrent relays. The first is the maximum load current. The relay's current setting must be above the maximum anticipated load current to prevent nuisance tripping during normal operation. Secondly, the fault current magnitude is important. The relay must be able to detect and respond to the minimum fault current level. Thirdly, coordination with upstream and downstream protective devices needs to be considered. The relay's time current characteristics must be coordinated with other relays and fuses to ensure proper selective tripping. There are different types of overcurrent relays available, including electromechanical, solid-state, and microprocessor-based relays. Electromechanical relays are the oldest type and rely on mechanical components to operate. Solid-state relays use electronic components for current sensing and tripping logic, offering improved accuracy and reliability compared to electromechanical relays. Microprocessor-based relays are the most advanced type, incorporating digital signal processing and communication capabilities. They offer advanced features such as adaptive settings, fault location, and communication with supervisory control and data acquisition, or SCADA, systems. The proper coordination of overcurrent relays is essential for maintaining system reliability and minimizing the impact of faults. Coordination involves selecting relay settings that allow the relay closest to the fault to trip first, isolating the faulted section while leaving the rest of the system operational. Coordination studies are typically performed to determine the optimal relay settings, taking into account the system's configuration, load characteristics, and fault current levels. Time current curves are used to graphically represent the tripping characteristics of different relays, allowing engineers to visualize the coordination between them. When a fault occurs, the overcurrent relay detects the excessive current and initiates a tripping sequence. The relay sends a trip signal to the circuit breaker, which opens and interrupts the flow of current to the faulted section. The tripping time is determined by the relay's time current characteristics and the magnitude of the fault current. Backup overcurrent protection plays a vital role in ensuring the safety and reliability of electrical power systems. It provides a crucial second layer of defense against faults, protecting equipment and minimizing disruption to power supply. The selection, setting, and coordination of overcurrent relays require careful consideration of various factors to ensure proper operation and system protection. Finally, let's address some additional considerations for breaker protection. Besides the three main protection schemes we've discussed, there are several other factors to consider for comprehensive breaker protection. Ground fault protection is essential for detecting and clearing ground faults, which occur when a phase conductor comes into contact with ground. Ground faults can be particularly dangerous and damaging, so sensitive ground fault protection is crucial. Ground fault relays are typically set to operate at relatively low current levels to detect even small ground faults. They can be either time delayed or instantaneous, depending on the specific application and coordination requirements. Breaker failure protection is another important consideration. Breaker failure protection is designed to operate if a breaker fails to trip when it is supposed to. This can happen due to various reasons, such as mechanical failure, control circuit problems, or communication issues. Breaker failure protection typically involves monitoring the breaker's status and initiating a trip signal to upstream breakers if the breaker fails to trip within a predetermined time. This ensures that the fault is cleared even if the primary breaker fails to operate. Overvoltage protection is also important for protecting equipment from overvoltages, which can be caused by lightning strikes, switching surges, or other disturbances. Overvoltage protection typically involves the use of surge arresters, which are devices that divert excess voltage to ground. Surge arresters are installed at strategic locations throughout the system to protect sensitive equipment from damage. Undervoltage protection is another consideration, particularly for critical loads. Undervoltage protection is designed to trip breakers when the voltage drops below a certain level, protecting equipment from damage due to undervoltage conditions. Undervoltage can be caused by various factors, such as faults, overloads, or voltage sags. In addition to these protection functions, it's also important to consider the breaker's interrupting rating. The interrupting rating is the maximum fault current that the breaker can safely interrupt. A breaker's interrupting rating must be sufficient to handle the maximum fault current that it could experience at its location in the system. It's also important to consider the breaker's coordination with other protective devices. The breaker's tripping characteristics must be coordinated with other relays and fuses to ensure that the breaker closest to the fault trips first, minimizing disruption to the rest of the system. Coordination studies are typically performed to determine the optimal settings for all protective devices in the system. Finally, it's important to perform regular maintenance and testing on breakers to ensure that they are functioning properly. Breakers should be inspected regularly for signs of wear and tear, and they should be tested periodically to verify that they are tripping correctly. Regular maintenance and testing can help to prevent breaker failures and ensure that the system is properly protected. By considering all of these factors, you can ensure that your breakers are providing comprehensive protection for your electrical power system.